Καλημέρα σας. Ελπίζω να μ' ακούτε όλοι. Χαίρομαι ιδιαίτερα που μου δίνετε η ευκαιρία σήμερα να συμμετάσχω σε αυτό το συνέδριο. Χάρη στον πολύ δραστήριο και ακούραστο κύριο Χαραλαμπόπουλο του τοπικού ASRAE Chapter και των συνεργατών του όπως η Ιωάννα και άλλοι. I think it merits repeating in English. I will make the presentation in English. I wouldn't be able to do it in Greek. So many thanks to the tireless and unstoppable, I would say, Mr. Haralambopoulos and his co-workers who continue to envision and execute world-class events like this one under the auspices of the local Hellenic ASRAE chapter, despite the many challenges, I might add. My presentation today will be a little broader than the paper that was contributed to the proceedings. I would like to explore the possibility of using these four newly registered ASRAE refrigerants, non-flammable, lower GWP type refrigerants, that may help the marine industry meet their sustainability objectives, and actually in the process also maybe save fuel and energy costs. The type of applications that I have in mind of interest to the marine industry are listed in this chart. We spoke a lot about refrigeration yesterday in the first day of the conference, both refrigerated containers and refrigerated vessels overall. Air conditioning, either for comfort duty or other cooling duty, such as cooling products and cargo. Water heating and steam generation in some of the larger ships to supply the onboard steam circuit. And finally, the generation of mechanical or electrical power on board to supply the electrical grid. For these two applications in particular, what I have in mind is accomplishing them by using low temperature heat from the main propulsion engine, which is usually an internal combustion engine, instead of wasting that heat and putting it to good use. So what is common in these applications is that they all consume high levels of energy, and in addition they have a high environmental impact, not only as a result of emitting carbon dioxide when combustion is used as the primary source of energy, but also releases of the refrigerant or the working fluid itself, which is used in all of these applications. A second common thread that ties these applications together is that they all can be accomplished with some variation of the classical Rankine cycle. The engineers in the audience may remember from the thermodynamics courses the classical cycle that is practiced in every power plant. Very briefly, an amount of heat is supplied to an evaporator to generate high pressure vapor, which then moves the elements of an expander, let's say a turbine, to generate power, and then the remaining heat is rejected at a lower temperature. An advantage when this cycle is practiced on board the ship is that there is always available a relatively cold sink to which to reject heat, and that increases the efficiency of those cycles. So the heat can always be rejected to seawater. And of course, if this cycle is run in reverse, you get the familiar refrigeration cycle that is used either to accomplish cooling or to accomplish heating as a heat pump. Finally, a third common characteristic is that the success of all of those applications depends on the proper selection of a suitable working fluid, which brings me to the heart of my presentation. Low global warming potential now has been added to an already very long list of requirements that the working fluid must meet. I'm listing them here. They pertain to, of course, performance, but also safety and environmental impact. going to let you read this at your leisure. But the key point here to make is there is no working fluid that can fully meet all of those requirements simultaneously for all applications. So we need to accept trade-offs and find an optimum balance in the selection of fluid for every specific application. You may be familiar with previous transitions in refrigerants and working fluids that the industry has undergone. The reduction first and then the complete elimination of ozone depletion potential necessitated the reduction first and then the complete elimination of chlorine from the molecules of working fluids and refrigerants. We're undergoing another transition now to a new class of refrigerants and working fluids, hydrofluoroolefins, which is characterized by the introduction of a double bond in the molecule of the refrigerant that facilitates the rapid decomposition of these fluids in the atmosphere and thereby leads to a low global warming potential. So let's see the four hydrofluoroolefin-based working fluids that I mentioned on the title page and how they can be used in various applications. Transport refrigeration obviously is of immediate interest for the marine and shipping industries. The fluid of choice for this application today, at least in the developed countries, is refrigerant 404A. This is a refrigerant with a relatively high global warming potential that exceeds 3,900. Also, I should mention that refrigeration applications in general, but even more so transportation refrigeration, which is subject to vibration and harsh conditions, tend to be highly emissive. So the replacement of this refrigerant 404A was one of the objectives of the F-gas regulation that has been recently adopted in Europe. The newly registered refrigerant R452A has a GWP which is now 45% lower than 404A. It is based on hydrofluoroolefin 1234YF. This is a new refrigerant that was originally developed for automotive air conditioning, but now it is adopted also for stationary applications. This new fluid is non-flammable. Non-flammability is certainly of high value on board ships where a fire or explosion can be catastrophic, and there are many restrictions to evacuating. What is quite attractive about this fluid is that it is a near drop-in replacement for the current fluid. So existing systems, refrigeration systems, can be easily retrofitted without any equipment modification or even lubricant change. And the energy efficiency of the new fluid is very comparable to the current fluid. So basically you accomplish the reduction in the GWP to comply with the F-gas regulation with a very easy transition and no loss of performance. Specifically for transportation refrigeration, a key requirement is that under fluctuating and often high ambient temperatures, the discharge temperature must remain within the specifications of the compressor. So there is a limit to the maximum discharge temperature that the compressor can accept. So there has been a study by a major provider of refrigerated truck and trailers, Thermo King, for this new fluid, the 452A, under a wide range of conditions, temperatures and speeds of operation of the compressor and so on, that has confirmed that the discharge temperature with the new fluid also remains very close, within 1 degree of the discharge temperature with the current fluid, the 404A. So the replacement also meets this demanding specification, which is particular to transportation refrigeration. So bottom line is that this fluid is a suitable replacement, lower GWP replacement for 404A, especially for applications where the lowest discharge temperature is required. For other refrigeration applications that don't require this tight specification on the discharge temperature, this fluid, also registered recently with ASHRAE, R449A, can be used. The advantage of this relative to the previous fluid I was talking, the 452A, is that it has an even lower GWP, so it moves further in the right direction in reducing the global warming potential. It is also non-flammable and also has the advantage of an easy retrofit. It's a near drop-in, again, replacement of 404A. But although those were the objectives, the primary objective in formulating this fluid was to reduce the GWP while maintaining close performance with 404A. However, the new fluid, as a bonus, achieves substantially higher energy efficiency as well. The energy efficiency relative to 404A, the incumbent fluid, is improved by 8 to 12% under medium temperature refrigeration, which is, say, up to -10, -15 degrees Celsius, and about 3% improvement in efficiency for lower temperature refrigeration conditions, we say -35 degrees Celsius, -40 in that range. All right, so moving to the air conditioning or chiller application, HFC 134A is the refrigerant of choice today that is used predominantly for, certainly for marine chillers. A new fluid has been registered with ASHRAE Committee 34, 513A. This is also a fluid that is based on hydrofluoroolefin 1234YF. It's a blend of this low GWP fluid with 134A, and achieves a GWP of 631, which is about 56% lower GWP than the current fluid, 134A. So again, it's a major step in the right direction of reducing GWP. Although it is a blend, it is a truly azeotropic blend, which has zero glide, which also explains the 500 designation of this fluid. This is significant for chillers because it's a requirement for the efficient operation of the large flooded heat exchangers of large chillers. And it also has a safety classification of A1, which means low toxicity, no flammability. Bottom line, this new fluid is a near drop-in replacement for 134A again. The theme in these fluids that I mentioned so far is they all achieve near drop-in replacement of the incumbent fluid, and they are all non-flammable, and they all move in the right direction of reducing GWP significantly. Although in the future we may seek to reduce the GWP even further, but for now it makes sense to take the step that is feasible today. More details you can find in the literature. And of course, this fluid can also be a replacement for 134A in refrigeration applications, although it was developed primarily for chillers, but 134A has also been used for many refrigeration applications, so 513A could be a replacement for those applications as well. Improving fuel efficiency, of course, has always been a priority for the shipping industry and marine industries in general, and also for the Navy. It can be viewed as a security advantage to require less frequent refueling. One approach to improving fuel efficiency could be to use the waste heat from the main propulsion engines to generate additional power from the same amount of fuel, so effectively increasing fuel efficiency. This new fluid, 1336 MZZZ, is suitable in accomplishing that goal, as I will discuss. But a few words about the fluid itself. This schematic shows the molecular structure of this fluid. The gray spheres represent carbon atoms, and you can see the double bond. So it has 4 carbon atoms. It's a fluorobutene. The blue spheres represent fluorine atoms, and the white spheres represent hydrogen. So this new refrigerant has been recommended for a safety classification of A1 again, low toxicity, no flammability by ASHRAE Standard Committee 34. I wanted to emphasize here that this new HFO hydrofluorolefin has a very low GWP of only 2, and it is non-flammable at the same time. It was discussed yesterday, and it has been discussed in other conferences in the recent past, that hydrofluoroolefins are mildly flammable. And this goes true regarding the first 2 hydrofluoroolefins that have been commercialized, but people were too hasty to generalize to the whole class of hydrofluoroolefins, making the erroneous assumption that the low GWP of these new refrigerants necessarily comes at the price of mild flammability. So this new fluid serves as a counterexample to discredit that myth. So you can have hydrofluoroolefins with very low GWP, almost negligible, and being non-flammable at the same time. I mean, hydrofluoroolefins is a very broad new class of molecules, and each one will have its own idiosyncrasies. I was going to make another quick observation. This molecule contains no chlorine. It contains fluorine, but no chlorine in its molecule, in contrast to other similar low GWP fluids that are now being commercialized. I emphasize this because we have found that the absence of chlorine dramatically increases the chemical stability of this molecule at high temperatures, which is obviously of critical importance for the application of interest here, which will expose the fluid to high temperatures. Again, I don't have time to discuss this in any more detail, so I refer you to another publication dedicated to the subject. If any of you are familiar with this application, it refers, the jargon in the literature is organic Rankine cycles. so it is nothing different than the standard Rankine cycle that every power plant practices, but the only difference is that instead of using water as the working fluid, you use an organic fluid, okay? So the incumbent fluid in this application is 245-FA, so it may be helpful to those who are familiar with this fluid to use it as a reference to compare the performance of the new fluid. This diagram shows you the vapor pressure of the 2 fluids of interest, the new fluid and the base fluid or the reference fluid. You can see that HFO 1336 generates significantly lower pressures, especially at high temperatures of operation. Of course, this is an advantage, as we will see soon. The complete thermodynamic behavior of a fluid is usually summarized and captured by the pressure enthalpy diagram. So let's run through a hypothetical application on board the ship that would use this fluid, the new fluid 1336, to generate power from waste heat. So let's suppose that we are going to extract heat from the exhaust gases of the engine at temperature such that we can maintain the inlet to the expander, let's say the turbine, the inlet to the turbine at a temperature of 225 degrees Celsius. So let's make some additional, hopefully sensible assumptions to fully define the thermodynamic power generation cycle. So let's suppose that the condenser of the cycle will operate at the temperature of 75 degrees Celsius. That would be a sensible choice when there is need and demand for heat on board at this temperature. So you extract power from the high temperature heat, and then you use the lower temperature heat to meet some other heating duty. If such a heating duty does not exist, then it would be of advantage to run the condenser at the lowest possible temperature, and again, access to the seawater allows a relatively low condensing temperature of 20 degrees. And the written paper to the conference presents an analysis for that case. But so let's take at this condensing temperature, maybe the subcooling will be 5 degrees and sensible efficiencies for the turbine and the pump. So the only other variable that remains to fully define the power cycle is the high side pressure of the cycle at the boiler. So in that value, it can be either below the critical or it could be above the critical. So when we analyze this case, the cycle thermal efficiency as a function of the high pressure of the cycle, it shows a maximum at a pressure of about 4 megapascal, or say 40 bar or so, which may be a more familiar unit of pressure, with a pretty attractive level of efficiency. It so happens that the maximum efficiency is accomplished for a pressure above the critical, but again, that is not an issue because this fluid generates low pressures, so even at pressures above critical, the pressures are still very manageable and easy to confine with common equipment components. And here is how the efficiency of power generation with the new fluid compares with the incumbent fluid. You can see, at least up to the sensible pressures that would be practical, the new fluid achieves significantly higher efficiencies than the currently available fluid, above 16% higher. So you accomplish a reduction of 99.8% in GWP, and at the same time you accomplish a 16% increase in efficiency. So that makes the new fluid pretty attractive. And in the last 2 minutes that I have left, I will mention another potential application using again the new refrigerant. One could use low temperature heat. On some ships there is need for steam generation, and now high temperature heat is used to accomplish that heat generation. Of course, high temperature heat is valuable, and I would rather use it to generate power. But then I would need an alternative way to generate steam, which means I need to heat water at temperatures higher than 100 degrees. And that can be accomplished again with a heat pump using this new fluid by providing colder temperature heat to the heat pump, and the heat pump then lifts that temperature to a level where steam can be generated. So just to give you a sense of performance for this concept, the usual metric for performance or energy efficiency that is used for these applications is the coefficient of performance. This is nothing else than the amount of heat that you generate over the amount of power that you consume to run the heat pump. Basically what you get versus what you pay. So with the new fluid, you accomplish significantly high values for the coefficient of performance for various condensing temperatures. So here we're talking about producing steam. So let's say you want to run the heat pump to produce steam at 125 degrees. Then the coefficient of performance or the efficiency for this operation would be pretty high, above 7.5. What that means is for every single unit of power that you consume to run the compressor, you produce 7.5 units of heat at the temperature you want, and no higher, because then it would be wasteful. So I'll close here and briefly summarize. So 4 new refrigerants have been registered by ASHRAE over the last few months, and each one has a specific target application. 452A will be a replacement for 404A in refrigeration and specifically transportation refrigeration applications. 449A is also a replacement for 404A that achieves a lower GWP than this fluid and lower energy consumption the attraction of this fluid is that it achieves lower discharge temperature. So each has its place. This fluid is a near drop-in replacement for HFC-134A. And finally, this fluid, 1336 MZZ, has the right combination of thermodynamic and chemical and safety properties to be used for waste heat recovery, both on board and for stationary applications as well. So thank you for your attention, and I'll be glad to entertain any questions you may have.
Έχουμε περίπου ένα λεπτό για κάποιες ερωτήσεις, αν θέλετε.
Is there anybody who wants to speak in Greek? I will speak English. I understand that this last week has rather high critical temperature, 171. A significant amount of heating on ships is available at low temperatures, below 140 and even below 90 degrees. Would you recommend this fluid for this type of system, for this type of fluid?
Yes, so
according to the graph, the efficiency will be very low.
Yes, so this fluid is more suitable for higher temperatures. If the available heat, well, it depends, of course, on what the application is. I think you are referring to power generation from heat, right? So for that application, if the temperature of the available heat is below 100 degrees, we have other fluids in our portfolio that would be more suitable with lower critical temperatures, indeed. We have a fluid I didn't talk about here. It's called DR14A with a critical temperature of about 111, and that would be suitable for converting heat available, let's say, below 100 degrees to power.
Is it possible to get some more information about that?
I'll be glad to provide, yes, if it's in your question.
I'm here with turbines in ships, exhausts are significantly higher, that can go up to 500, 400 degrees Celsius. Are there any other fuels that even go higher than the 170, which is on the way? Which means that we can make use of the heat more, that's getting exhausted.
Yes. When the heat is available at such high temperatures, say higher than 300 degrees or 400 degrees, water is the best fluid, which is very stable, is cheap, is safe, and practically efficient at those high temperatures. It is when the available heat is at lower temperatures, say lower than 300 to 250 degrees, that an organic fluid is advantageous.
Before when UTC was making works on the 200-liter cycle, they only went up to a quarter of a megawatt. But the company in Italy, they're making a much bigger turbine. Have they, on larger units, have they made them with lower temperature heating when you're talking about
I do not know. I cannot speak for turbine.
or is any company made any large works?
For power generation from heat below 100 degrees. Is that the question? Well, of course, I do not know. I know what our close partners are working on. I do not know what everybody is working on. But publicly, to the best of my knowledge, there is no commercial application. So there are some applications that I have heard on limited scale that use 134A. Of course, as you realize, the hurdle for such low temperature heat is that the Rankine cycle efficiency is intrinsically very, very small, limited by thermodynamic purposes, thermodynamic reasons, regardless of what the fluid is. So the little power you generate must be very valuable to justify this application. So there are niche applications, but not to a very large scale that I know of.
I mean, as NSC said, there's on the ships, you have a lot of very lower temperatures. But it's the higher temperatures that are used for generating water and generating steam production.
Yes, but what I was proposing today as a possibility is that instead of using this valuable high temperature heat, let's say you have heat available not at 500 degrees, but let's say at 250 degrees, right, in the exhaust gases. It would be thermodynamically more effective to use that heat to generate power to convert to power, which is more valuable, and then use the low temperature heat that you have available in the jacket cooling water of the engine, for example, which is below 100 degrees, use that with a heat pump to generate steam.
What would the total losses be on that?
A total loss?
Yeah.
How do you define the loss?
This is by converting it, what would the total COP be?
The total COP, at least the ideal COP, so if you look at this example, let's suppose you take heat from the jacket water, which is at 90 degrees, right, roughly, and you use a heat pump to lift it up to 125 degrees to generate low pressure steam. Okay? So in this case, the theoretical COP will be 7.6, 7.7, which is a very high COP. Now, the actual COP, which accounts also maybe for frictional losses and the heat transfer losses, will be a little lower than that, but still very high and very attractive.
I mean, if you put this in series with taking the heat from the exhaust gas, is the COP on the earlier or emissions is only 20%?
Yes.
Go from 20% to 7%.
But those are the different measures of efficiency. I don't know that they can be edited. So overall, the steam we produce out of the exhaust heat, whatever amount that is, 20% of that or 15% of that will be converted to electricity. And then you will use the jacket water to produce a certain amount of steam. So to specifically examine whether such a scheme would make sense, somebody needs to do the quantitative analysis for a specific situation, right? To know how much heat goes to the exhaust at what temperature, how much heat is needed for steam generation, and so on, and take into account the cost of the equipment and see if the efficiency gains justify the investment of the equipment. What I know to encourage such a study is that this concept, both of those concepts separately make sense and they're commercially attractive and they're being pursued. Specifically, the Rankine cycle of converted heat from exhaust from an internal combustion engine is attractive for trucks to improve the energy efficiency of trucks. So that's encouraging. It doesn't guarantee that it will make sense also on board, but I guess my objective is to motivate somebody to take a look.
Okay, now we can take a coffee break. Thank you very much.